is Timo, and he will talk about asymptotic inference for score decompositions.
So thanks a lot, and thanks a lot for giving me the possibility to speak here. What I'm presenting today is joint work with Marius Puke, who's a doctoral student in Hohenheim. So let me jump right in. So we go from the overall topic of probabilistic forecasts a bit more rough to point forecasts. So what we're looking at is is a real valued outcome variable of interest. That might be, I'm an economist or econometrician, so I'm often looking at financial or economic data, so financial returns or inflation rates, and we have a point forecast. You can think of that as a mean forecast, but it might also be a quantile forecast, but then it gets a bit more complicated. Then the overall notion of calibration or reliability we're looking at for mean forecasts, I mean, you saw that during the week already quite a few times, is that the expectation of our outcome given the forecast is x is exactly x for all x on the real line. So that means whenever inflation rates are forecasted to be 2%, among all these quarters, we expect that average inflation is roughly 2%. So that's the notion of calibration for mean forecasts, and more generally, forecasts can be taken at face value. So if you see 2%, 2% is what you can expect, and you don't have to remodify to 5% or something. And as we've already seen, calibration is not all there is to a good forecast. There's also the important property, or even more important, I would say, of discrimination, that forecasts can distinguish between, in my example, high inflation rates and low inflation rates. So let's jump into one motivating case study I have, and that is forecasting financial volatility. What we have here, YT is a series of S&P 500 futures, and here I plot the squared return in gray, so because we talk about volatility. Then I have two competing forecasts. One is the Gauge and one the Haar. You don't have to know what these forecasts are. They're just two competing one-day ahead forecasts for the financial volatility or variance the next day, in color here. And you see a bit of a difference. Now, what do economists classically do if they want to evaluate that? One thing is they run a calibration test, and the most famous one is going back to Minz and Sarnowitz more than 50 years ago. And what you would see here, if you look at the p-value of that Minz and Sarnowitz test, the Haar model is clearly rejected, so it's not calibrated, whereas the Gauge model is not rejected, so it might or might not be calibrated. Bold numbers indicate the better model in this table. However, economists also, what we also propose is compare strictly proper scoring rules for scoring functions in that case, and the Q-like score is one of those. And there, the Haar model has the lowest score and is favored. So it's kind of a discrepancy in that example that, well, the calibration test favors one model, whereas the score evaluation favors another model. And so, especially like the banking regulation, is building a lot of these back tests or calibration tests. And I would say that's a bit problematic, as they might favor the wrong model. So what we do is we look at score decompositions. That is, we look at a decomposition of the score into miscalibration, discrimination, and some uncertainty term, which is not that important. And this already gives us a solution to that puzzle. That is, well, the Gauge forecast has a lower calibration component, or a lower miscalibration component, so it's better calibrated, whereas the Haar forecast has a higher discrimination component. It must be higher to be better, so that is favored. So that means, and these add up to the overall forecast performance, so that gives us a clue what's going on. And what we often look at are plots like this what we call a miscalibration discrimination plot, where we have miscalibration on the x-axis, discrimination on the y-axis, and so the score is a difference of the two. So a higher score means you have to be up in that direction. Sorry, a lower score, a better score as you're in that direction. And all the forecasts on that line have the same score, and all the forecasts on that line have the same score. So you see the same thing. Well, Haar is a bit further to the upper left, so it has a better score. Gauge is further to the left here, so it has a lower miscalibration, but Haar is much better in discrimination. All right, but now a question you could ask, are these differences in the score decomposition significant? And that's exactly what we're looking at. So we're looking at asymptotic inference in these score decompositions. All right, so let me start with reliability diagrams and score decompositions. So what do you do if you plot a reliability diagram for mean forecasts? So what you want to assess is the expectation of YT given the forecast is x, exactly x? So if you plot x, the forecast, against this conditional expectation on the y-axis, this might be this curved line here for these forecast realization pairs, and you check if that's the diagonal or not. Okay, that's not too complicated, I would say. For now, this is simply population, so assume you know this conditional expectation. Okay, in practice you don't know it, so you have to estimate that somehow. What you can do a linear regression. This imposes a model misspecification here, but okay. And this more or less leads to this test of Mintz and Sarnowitz. They simply test whether that linear recalibration line is a diagonal. You can do isotonic regression or some other non-parametric kernel regression, or other things you might want to do. And so what do you do in practice? Well, this is more or less a bias variance trade-off. If you do isotonic regression, this is non-parametric and flexible, but if your true recalibration function is nearly linear, then maybe the linear approximation is not so much of a bad fit. And especially in econ, the signal-to-noise ratio is often quite low in the forecast, so we argue that linear decomposition is often doing a good enough job, I would say. All right, so we will do linear estimation later on. You've got a hint already. So let's now talk about, from the reliability diagram, how do we get these core decompositions? Johanna hinted on them already a bit in her discussion, but not for mean forecast, but for, I think, binary classification. So this core decomposition is quite easy if you look at it up here. So what we do, we add and subtract the blue recalibrated score, and we add and subtract the purple reference score, and so this equation holds naturally. And what is it? The forecast score is the expected score of the forecast and the outcome. The recalibrated score is the expected score of the recalibrated forecast, which is the conditional expectation of y given x. And the reference score is the score of some unconditional but calibrated forecast, so it's simply the unconditional expectation or unconditional frequency or the unconditional expectation what you have. All right, now why does that measure miscalibration? What you see here, this is a score improvement under recalibration. So how much does your score improve after I've recalibrated with the information that's in my forecast? So if that's high, then you gained a lot by recalibration. Your original recalibration was bad. If you don't gain anything by recalibration, you were already calibrated. Okay, now why does that measure discrimination? Here we see how much does our recalibrated forecast, having the information of the forecast, improve upon a forecast that doesn't have any information, so it's just unconditionally flat. So how much information is there really in your forecast? And what you did by comparing this recalibrated to the reference forecast, you take calibration off the table. Both are calibrated, one with the information of the forecast, one without information, and you measure how much is one forecast better than a forecast without information once calibration is taken off. So that's a pure measure of discrimination, ignoring calibration. And then you finally have the uncertainty term. This is boring because there's not even an x in that formula, so this is just constant for all forecasting methods, and it's kind of a normalizing constant. All right. Now, we want to estimate the recalibrated forecast, and we do that by, as I already said, linearly regressing y on w, so that's a vector containing an intercept, the forecast, and you can add other variables if you want to. We're not going to talk about it in this day. Motivated by the low signal-to-noise ratio we have often, and I mean, economists like that. It's related to this Mintz-Sarnowitz test. So in the end, everything you see here is the finite sample versions. So we have a hat, that's an empirical score decomposition, we have hats everywhere. The forecast is simply the average, the forecast score is the average over the scores. The recalibrated score is the average over the linearly recalibrated one, and WT theta t is the linear regression estimate, and RT is simply the unconditional average. And so what you already see, we want to do inference in the end. There are two sources of uncertainty. One is we have to approximate the expectation with this average, and the second one is we have an estimation effect that theta t is estimated, so the linear line is of course not known. All right, so what do we get? Assume that the true miscalibration and discrimination with a bar are the population versions for us. we didn't want to use another index 0 because we have so many indices already. So even they're greater than 0, this might be a bit restrictive. Let's see. And under some regularity conditions, which are weak, I would say, so we have the linear recalibration is the true one. That's maybe not so weak. Stationarity, alpha mixing, finite moments, and the loss function must be equicontinuous. Then we get a joint asymptotic normality of this miscalibration of the first forecast, the discrimination of the first forecast, and the same for the second. We need this joint asymptotic normality to conduct tests that minus that is 0. So we can test of equal miscalibration and equal discrimination by this joint asymptotic normality. I mean, this is not rocket science, it's asymptotic normality. What's quite nice is that the estimation of the recalibration is orthogonal in the sense that it doesn't enter the asymptotic covariance sigma t. So if I go back, I told you there are two sources of uncertainty. This unconditional this average and this estimation doesn't enter the asymptotic covariance matrix because it's orthogonal in the other estimation effect. So it's quite nice, I would say. And this also would give rise to semi-parametric estimations, so you can estimate it non-parametrically, and as it's orthogonal, you don't get a problem in convergence rates. It's getting a bit more difficult if you have non-differentiable loss functions for quantiles, but I think that's manageable. So, second asymptotic theorem. Well, I told you in the first one that we need the condition that, that the miscalibration, the true one, is greater 0. So it means it doesn't work for calibrated forecasts. That's a bit of a problem. So what happens if we actually have calibrated forecasts, or if they're perfectly calibrated, then we see that's an inference problem on the boundary, because miscalibration is always positive or 0. So that hypothesis is on the boundary. And then we get an asymptotic with t as a convergence rate. That's no super consistent estimator. It's just because things are squared up. And we get a generalized chi-square distribution as the asymptotic variance. You don't have to read these formulas. So now the picture turns in that this asymptotic uncertainty is purely driven by the estimation effect. So, and that's where we also get this higher order there. Yeah, we have a different convergence rate. If you think in the beginning I was happy and thought, oh, that's a nice calibration test with a convergence rate of t instead of square root t, but that's not true. I was overly optimistic, so it behaves exactly as the Vincent-Samuels test. We only do that for smooth losses so far because the equicontinuity is a bit harder with this t. And you get something very similar if the discrimination is 0. Then the discrimination parts converge to some asymptotic chi-square distribution. Same story, just a bit more complicated because you have to estimate two things: the recalibrated forecast and the reference forecast. All right. Now, if we want to test, for example, the hypothesis that two miscalibration components are the same, we don't know whether they are truly 0 or not. So what we do, this hypothesis is equal to the hypothesis that they're larger 0, union, the first is 0, intersection, the second is 0. So you split it into being 0 and not. And then, well, we have an intersection, union, intersection testing procedure, so we take the max and min of the p-values. And luckily, the final p-value usually coincides with this p-value from the asymptotic normality. So these corrections, they don't hurt as much. All right, then I would like to quickly give you simulation results. The first case is everything's equal, so scores are equal, discrimination is equal, miscalibration is equal. The forecasts are still not collinear, so we added some random noise to those. We get, they don't reject, so you have sample size on the x-axis, rejection rate here, so test works asymptotically. Second case, discrimination is equal, but miscalibration is unequal, and the only difference in scores comes from the difference in miscalibration. Now we see the discrimination test still has no power, that's nice. The score test develops power, and what's quite nice is that the miscalibration test is more powerful than the score test. How I explain that is that if we only test the miscalibration, then we kind of take the uncertainty that's in the discrimination off the table. And by that, we get higher power. That's my interpretation. Because we try to balance it that the effect sizes are similar, and we see something like that in the application later on as well. And something very similar happens in case C, where miscalibration is equal, discrimination is better for one forecast, and that causes the score being different. And then we also see that the discrimination test in red has a bit more power than the score test. And I told you that the estimation effect of the recalibrated forecast is orthogonal to our asymptotics, meaning that this additional uncertainty we have by the estimated recalibration doesn't enter our uncertainty in here, because this would destroy our power, I guess. So I'd like to show you two applications in the last 4 minutes. Sorry, yeah, I need to speed up, sorry. So the first one is the financial volatility forecasts I motivated everything with. So what we see there, all right, all three score, the score is significant, the discrimination is significant, and the miscalibration is significant. So we can actually explain the difference between the Minzer-Zarnowitz and the final test by that. Now, I'd also like to show a second application, that is, we look at inflation forecasts, and there are often two survey forecasts people look at. The first one is a survey of professional forecasters. These are professionals that forecast inflation rates, and they should be better than the people answering the University of Michigan survey of consumers, because these are ordinary people, and they should hopefully know less about inflation than the experts. But if you look at that, classical papers about that, or which consider that, find no significant difference in the forecast performance. So if we put the scores of the Michigan, the SPF, on this miscalibration discrimination plot, you see that, well, in miscalibration they're quite equal. However, the discrimination of the survey of professional forecasters is much better than that of Michigan. Makes sense, they have more information. They forecast better. Now, if we apply our tests, we see scores are not significant, as the other papers find. Miscalibration is not significant. All right, this was to be expected. But the discrimination becomes significant. And that I explain by taking off the uncertainty or the variance that the miscalibration gives the scores. And if you focus on discrimination, you can actually get a bit of a higher power. All right, so as a quick conclusion, scoring functions combine both calibration and discrimination additively. If you only do calibration tests, what economists often do, you miss a substantial source of forecast performance, that is discrimination. We use linear regression to recalibrate in the evaluation. This doesn't make sense in a binary case, but in a mean case, I think it makes sense. And then this can be applied to many forecasts, and we're planning to do it also on quantile valued risk forecasts, but that's not done yet. So thank you very much for the attention.
Thank you very much for the presentation. I think we have time for one or two questions right now. Yes, please.
Hi. Thank you for the presentation. So I have maybe two very quick questions. The first thing is that how did you recalibrate the Gaussian model? There's no regrets, right?
Oh, we take the forecast of the Gaussian model, and then we simply, in the out of sample period, you take the forecast.
Square the return.
We use the squared returns for, yes. We think of the Gaussian volatility forecast as forecast for the second moment, so it's an expected value forecast for the squared return. And then we recalibrate it like that.
Right. So you did the same thing for half?
Yeah.
Okay, right. And another question is that in your hypothesis testing, I mean, you have multiple objects, right? So my own experience is that when you do that, if you have loads of objects, in this case you have 4, you might have size distortion. Did you adjust for that?
You mean the asymptotic normality where we have 4?
Yes. Did you have size issues?
I don't think so.
Right, okay, that's cool. Yeah.
I've like slightly, as you usually have in asymptotics, that you have like 12 instead of 10%, but it's not severe, I would say.
Yeah, thank you.
Good. I think we would ask Mark to set up so that we can switch over in time. And we have time for more questions also during the discussion.
Thanks.
Thank you, Timo.